Okay, so we're going to look at another circuit here that we've examined in our first circuits course. And this is going to be Vn, and then we're going to have a coil, or an inductor, capacitor, and a resistor. So this is a series RLC circuit. So L, C, and R. And we're going to take the output across the resistor. And so I'm going to kind of do the transfer function, but kind of skip it a little bit here. So let's go ahead and look a little bit here on how we would find it. Well, first off, we would do Laplace domain and get L times S, and then 1 over S times C. And then this is just a series circuit, so we'd also, of course, let the input be delta at t, which goes to 1 for my Laplace transforms, and because that gets me that my output voltage is just equal to my transfer function. And so V out would simply be R over S times L plus 1 over S times C plus R, and of course times 1. Now, this isn't too hard to do the arithmetic for and everything and clean things up. I'm going to skip all of that work here and just say, okay, it's only like 3 or 4 steps actually, tiny bit of algebra, and we get a transfer function that is equal to R divided by L times S divided by S squared plus R over L S plus 1 over LC. Okay, so now we have to kind of do some messy work here, because what we really need to look at is we want to look at the magnitude of h at j omega, because we want to find these 3 dB points. So we're going to go ahead and substitute that in. So we'll look at h at j omega, which is R over L times j omega divided by j omega squared plus R over L j omega plus 1 over LC. Now if I take the magnitude of this, I'm going to do the magnitude of the numerator, but let's just go ahead and write this off to the side. The magnitude of R over L times j omega is just simply going to be R over L times omega, because there's only an imaginary component in the numerator. Now, the denominator, when we take the magnitude of that, it's a little bit more complicated. First off, let's recognize that this right here is negative omega squared. Okay? So, what we have, and this is a real number. There's no longer a j there because j squared is negative 1. So, the magnitude of my denominator, I'll put magnitude of denominator, is going to be equal to the square root of 1 over LC minus omega squared, quantity squared, plus omega times R over L squared. Okay. Now, this is where the fun stuff comes in. We need to find equations for omega 0, omega c1, omega c2, beta, and q in terms of R, L, and C, because we want to be able to design a circuit that has these parameters. Well, there is one special thing about omega 0 that we didn't talk about previously, is that omega 0 is the frequency where h at j omega is purely real. So I'm not going to look at the magnitude. I'm actually going to go back and look at h at j omega here, and it being purely real. Well, let's even simplify this a little bit more here. So omega 0 is the frequency when h at j omega is purely real. Let's look at here what my V out was. It was R over SL plus 1 over S times C plus R. So to be purely real, we need SL plus 1 over SC to equal 0. Because then these are where the imaginary parts are going to come in, right? Because that's the j omega. So in other words, let me write this out again here, substituting in R. We were thinking about like steady state, j omega L plus 1 over j omega C plus R times 1. Now to be purely real, again, this term needs to be equal to 0, because then we just have R over R, which is purely real. So there's no imaginary component to it. Alright, well, what do we do here? Well, we have j omega L plus 1 over j omega C is equal to 0. Well, just remembering things here, this would be the same thing as minus j over omega C equaling 0. So solving this, we get j omega L is equal to j over omega C. Omega squared is equal to 1 over LC. And so these actually should be omega naughts here. So omega naught, or my center frequency, is the square root of 1 over LC. So this is our first critical equation here. Critical. Now if I look back at my transfer function here, let's look at something here on my transfer function. Look, I've got 1 over LC here. So that's actually omega naught squared. Okay, well now we need to find, the 3 dB points. Well, we have the transfer function here that we have omega c times r over L. This is the magnitude of h at j omega that I'm writing here. And this is all over that really messy square root, that denominator square root that we found. So this would be 1 over LC minus omega c squared and this is omega c squared there as well, plus omega r over L squared. That's what we'd have, and this is omega c. And what does that need to equal? That needs to equal 1 over the square root of 2. And why does it need to equal that? Because again, this is my half power term. Okay, so half power, great. Oh, well, this is kind of an ugly thing to have to deal with. I mean, obviously I could square both sides, so let's go ahead and square both sides. So you'd have omega c squared, or instead of writing that, omega c r over L quantity squared over 1 over LC minus omega c squared quantity squared plus omega c r over L squared is equal to 1/2. Now I'm going to skip solving this because it's just a bunch more algebra, but you wind up with you're going to have to do a square root here at some point. You're going to wind up essentially with a quadratic equation. So if you wind up with a quadratic equation eventually, going through all the work here that I'm skipping, what you wind up with is that omega c1 is equal to negative r over 2L plus the square root of r over 2L squared plus 1 over LC. And that omega c2 is equal to r over 2L plus the square root of r over 2L quantity squared plus 1 over LC. Okay. And if you actually multiply these together and take the square root, you do wind up with 1 over LC. Now, the nice thing here is let's look at beta, because we're going to get an equation for beta here. So again, let's look at important equations. These are important. So beta here is equal to omega c2 minus omega c1. Now, let's just think about subtracting these two equations. Well, these terms here, these square roots are just going to disappear, and you're going to wind up with r over 2L minus a negative r over 2L. So this just actually becomes r over L. Well, that's convenient. And so let's remember, we also have omega naught being 1 over the square root of LC, or the square root of 1 over LC. Doesn't matter which way you write it. Right? We've got that. So then Q, remember, is omega 0 over beta. So this would be the square root of 1 over LC divided by r over L, which just doing some basic algebra simplification, you get that this is equal to the square root of L over CR squared. Okay, so we get that there. Now, we have a set of 5 equations here again, but now we have to think about it. I know this video is going to go a little bit long, but let's look at the difference in designing bandpass filters. And what do I mean by the difference in designing them? Well, we had one circuit that we did in the previous lesson. Actually, I'm drawing it wrong here. It was this way. So this is C2, R1, R2, C1, R1. And we had very simple equations. Omega C1 is equal to 1 over R1 C1, and omega C2 was just equal to 1 over R2 C2. But now we have a different kind of bandpass filter. Still a bandpass filter, but it's using different components. And let's think about designing this one here. If we had omega C1 and omega C2, these would be a pain to use to find R, L, and C. But wait, let's look at some other equations that we have here. Some simple equations that we have. Quite frankly, the simplest equations we have here are this one, because bandwidth is just a resistance divided by an inductance, and then my center frequency is 1 over square root of LC, and so we can get these components. So depending on the type of circuit, you might want to use different parameters for the design. And in the next video, we're going to do a design on this bandpass filter to illustrate what I'm talking about.